Alright, logicians, so in this video I'm going to talk you through how to use an indirect truth table in order to determine whether or not two statements are consistent with each other. So in past videos in 7H.II, we talked about how to use an indirect truth table to determine whether an argument is valid or invalid. And when we do that, we're treating the argument as if it's innocent until proven guilty, and we're looking for a counterexample to show that it's not valid. With consistency, we're doing the opposite. We're trying to find just one line on which both of the statements are true. And that's the one piece of evidence that we need to show that the two statements are consistent with each other. So what we're looking for is, can I make this true and this true? And if you can find a set of values under which both of these are true, you've shown they're consistent. But if no such possibility exists, then they're not consistent. All right, so again, we want to start with the line which gives us the fewest possible ways in which it could be true. We want to save ourselves work. So there are three different ways in which a horseshoe could be true, right? Three different lines on the horseshoe truth table in which horseshoe comes out true. So that's three options to work through. There's only two ways in which a triple bar can be true. So that's still two options to work through, but let's start there. And let me say, I invented this problem just before I turned on the camera, and I haven't worked it out yet. So I don't even know how hard it's going to be. But anyway, I'm going to start with this line. Okay, in order for a triple bar to be true, either both sides can be true, that'll make it come out to be true, or both sides can be false. So I'm going to work through both of those. So I'll make not Q true, that's going to be one line, and not S will be true. And that means that Q itself is false, and S itself is false. And then the other line is they'll both be false. That is that the negations will both be false, which means that the letters themselves will be true. Either one of those will make our main operator triple bar turn out true. Okay, so let's start with the top line first. So Q is false and S is false. I'm going to plug this in over here. And then on the next line down, Q is true, S is true. And let's see what that does to this. So let's start with line 1. If Q is false and S is false, then I know already that the wedge, that this junction of those two, is false. Right? Because neither one's true. Now, that is actually good news for me, because if the antecedent of a conditional is false, then the conditional itself is true. So, bingo. You know what I've got? I've got a combination of truth values here under which this line is true, this statement is true, and this statement is true. And I have shown that therefore these statements are consistent. I don't even have to work out, the second line. Although for kicks we can see what that does. So if they're both true, Q and S, then the wedge is true. So then we have to figure out, well, is the conditional going to be true? Only if this conjunction is true. Because we got to have it if true, then true. So in order for this to be true, then not R has got to be true, and P's got to be true. And if not R is true, that means that R itself is false. But we can do that. So if we've got, let's see, R is false and P is true. And look, on this line of the truth table as well, we can make it come out true. So that's another line that shows the consistency of these two statements. But you only need one of those in order to do it.